Hey Sherwood. In this lesson, we'll be looking at connections between the derivative function and the function itself. And what I've done is I've taken example 4 from page 209 to present. And so you're welcome to also read in your textbook if that helps you learn the material as well. Okay, so the question we'll be exploring is what can we learn about a function by examining the graph of its derivative? And here we're presented with the graph of the derivative function, not the function itself, but its derivative. And we'd like to make some inferences about the original function. So just some information that we like to learn about functions in general. We like to know where a function rises and where it falls. We like to know where the graph bends up and where it bends down. We like to know if there's any local high points or any local low points. And we like to know where those points of inflection occur. Shoo, shoo. Okay, so let's see if we can seek out this information for this function using the graph of the derivative. Here goes. Where's the original function increasing? Where's it decreasing? And how are we supposed to tell given the graph of the derivative? Well, let's step back for a moment and ask that question generically, and then we'll examine this particular problem. By the way, a measure of whether you're understanding the material in this section is your ability to predict the words that are coming up on the screen. If you really know your stuff, you should be able to guess the words, and if not, then you should probably hit the books and really master this material. Okay, so function is increasing when its derivative is positive. The slope is positive where the function is increasing. And similarly, the function would be decreasing if its slope is negative. So that's what we're going to look for. To tell where the original function is increasing, we'll watch where the derivative is positive, and to tell where it's decreasing, we'll see where its derivative is negative. Okay, so with that in mind, let's go ahead and answer the problems. Where's the function increasing? Where's it decreasing? And to help with this, I'm just going to write in some values. At -4, we're up here at like 13. Here we're at like 2 point something, 0, close to 1, a little higher than 1. Here I'm at 0. Here I'm at almost -3. -4 approximately, 0. And up here we're probably at like 15 or something. Okay, so with that, let's see when is the derivative positive, and that will tell us where the function is increasing. Well, this is positive, still positive, 0. All in here, we're above the x-axis. These are all positive values for the derivative. Still positive, 0 again, and now we're finally getting some negative values for the derivative. All right, so with that, let me clean this up. All right, anytime the derivative is positive, which is all in here, we're going to expect that f of x is increasing, all in here. And anytime f prime is negative values, we're going to expect that f is decreasing, all in here. And it looks like we're increasing again where the derivative is positive. So increasing again from that point onward towards infinity. Okay, so let's summarize this information. From the left end of the number line right up till here, which is 1, the graph is increasing. And between 1 and 4, the graph is going to be decreasing. And then from 4 on out, we'll expect f to increase because the derivative is positive. All right, and let me actually go to the summary screen. So I'm going to jump ahead. At the end of this task, we want to know what the graph looks like. And we just determined that there are important changes that occur at 1. So let me try to line that up properly. Okay, when x is 1, something interesting happens. When x is 4, something interesting happens as well. And in particular, we've learned that on this interval from -infinity to 1, we should expect f of x to be increasing. Between these two values, it should be decreasing, and from 4 and forever, it should be increasing again. All right, now one point that I didn't really mention was that it does actually reach 0 here, so strictly speaking it's not positive, but let's picture what the graph will look like at that point. Positive slopes have increasing values. Now it's 0 slope, so flat point like that, and positive again, so it's like that. So it's actually really increasing the whole time. All right, so nothing to worry about with that. Let me just wipe that clean for you. Okay, so we've answered the first question in terms of where the graph rises and falls. Now it's time to step it up and talk about the concavity. Is the graph bending up or bending down? Well, here's a necessary theory that a person needs to know to answer this question. And again, if you can predict what I'm about to uncover, then you know your stuff. Okay, what does concave up mean? Well, visually, it means the graph looks like that. And in terms of slopes, we see that the slope is a negative, now 0, now positive, now a higher positive number. The whole time the slopes of these lines are actually increasing. So that's the definition of concave up. All right, f prime is increasing, the slope is increasing. All right, whereas, just the opposite now, what does it mean for the function to be concave down? It means it looks like that, a cup that points down. Pointing down, concave down. And so right there, the slope should be decreasing. Slope's a high number, lower, lower, 0, and it keeps decreasing from there. All right, so if the slopes are decreasing, if the derivative is decreasing, then the original function is defined to be concave down. All right, so when we go to this graph, we're going to look at places where the derivative is increasing, and we'll infer the original graph is concave up. Look for where the derivative is decreasing, and we'll infer that the original graph was concave down. Let's do it. All right, so again, we started from something up around like 13, and we're decreasing, dropping, 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 all the way down to 3, dropping, 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 all the way down to 0. So all along this red part, the f prime is decreasing, and that tells us that our original function is going to be concave down because f prime is decreasing. All right, and then we'll do a little switcheroo here. Now I'm rising, getting higher, higher, higher from 0 all the way up to like 1.2 or whatever. And since the derivative is increasing there, we can infer that the original function must be concave up in that interval. Okay, and now more of the same. We're decreasing down to 0, decreasing to negative values, down to here, decrease further, all the way down to here, and then we're coming back up. So that tells us that right up until this value, we're going to see a graph that is concave up. And now we're back to rising again, rising to 0, rising all the way up to here. And so wherever the derivative is increasing, we should expect that the original function is concave up because its slope is increasing. All right, and again, let's pop over to the summary screen where we're collecting all of our information. And what have we just learned? We've learned that regarding concavity, something interesting happens here, where it goes from decreasing to increasing. So I'll label -2 as an important number on our number line. And we'll write in that between these values, we're expecting the graph to be concave down. Okay? And we might as well, as we go through, we might as well start to envision what the graph looks like. So we're going to start combining information. We know, number 1, that the graph is increasing, and number 2, that it's concave down. Increasing can happen one of two ways, but only one of them is concave down, and it's this one. So I'm going to go ahead and start sketching this graph. Increasing concave down should look like that. Okay. All right, so with that, let's keep on rolling. We have, in this interval right here, I'm increasing now right up until there. So 0 is an important number. And since f prime is increasing, we said that the function must be concave up. Okay. And it's still increasing right there. The graph is increasing, but this time we're concave up. So let me circle the one that's increasing and concave up. So it should look like that in this interval, increasing and concave up. Okay, next, just keep going with that. Here we're decreasing all the way down to here. All right, at 3, something interesting happens, so let's put 3 down. And the derivative is decreasing, so that tells us that the function is concave down. But this time in this interval, we're now, well, it looks like there's a changeover, so maybe I better slow down and be careful. All right, to the left side of this dotted line, I'm concave down, but I'm increasing. So let me make a picture of that. Clean this up. Okay. A graph that's concave down looks like that, but it can either increase or decrease. And we want the part that's increasing. So I'm going to draw a shape like that, where it is increasing but concave down. Let me just do it here. Increasing, concave down. And then to the right side of the dotted line, we're still concave down, but now we want to be decreasing, because that's what's supposed to go on in this interval. So let me make a picture of that. I'll just keep cleaning this area up. All right, so I want to draw a graph that's concave down, and I want it to look like the part that is decreasing. So that would be this shape. So now I'm decreasing, concave down. All right, and back to the original graph of the derivative here. From 3 and on up, we're increasing, increasing, increasing. And if the derivative is increasing, then that means the function is concave up. So I'll write concave up here. And now we know that to the right of 3, the graph should be concave up. It's also decreasing there. So again, let's clean it up and picture what the graph looks like. Okay, so I'm drawing a graph that's concave up, and I'll select the part that's decreasing, because that's the information that we have about it. So it should be decreasing and concave up. Okay, but only up to, I've gone too far, only up to this value of 4. And then we have this change where we determine that it's now increasing and concave up. So it's going to look like this part, increasing and concave up. So that part of the graph should look something like this. Okay. Now, if we felt like it, we could probably assemble all these little miniature curves into a decent graph. But first, let's go and seek out some additional information about the maxima, minima, and inflection points. All right, let's see what we can learn. So back to business here. We'd like to know if the function has any local extrema, local highs and lows. And so we know that a function has a local maximum where certain things happen. In particular, the derivative changes from positive to negative. And that's our first derivative test. On the other hand, we should expect to see a local minimum where the slope changes from negative to positive. Again, if you're able to tell these things before they're revealed on the screen, you really know it. And if not, you really need to review it and study it until you really master it. Okay, so in search of local max, we'll look where f prime changes from plus to minus. And in search of local min, we'll look for where f prime changes from minus to plus. Let's go ahead and look at the graph of the derivative and see where those interesting things happen. Here goes. So here's a positive value to 0. There's no sign change happening yet in the derivative. Okay, here's a positive, here's 0, and here's a negative. Yay. All right, so right in here, we have positive, 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 0, negative, 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 negative. So right there, the derivative is changing its sign, and so that signals that the original graph has a local something or other. And let's picture it. Positive to negative looks like this, positive to negative. So that's a local max. All right, local max at this x value, which is 1. And let's keep rolling. Okay, next. These are all negative values, negative, 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 negative. Let's still negative, still negative, still negative, 0. And now we're positive values. Okay, so it changes from negative to positive at this input, which is 4. And let's try to describe that. Negative derivative to positive derivative means negative slope, positive slope, and that should look like a local min value. Local min. Okay, so there you have it. 1 and 4 are the important numbers here. Max at 1, min at 4. Let me assemble those facts on my summary screen. Okay, so, and I'll just scoot this question out of the way for the time being, if I can do that. We said that there's a local max, so I'll just put max here at 1, and a min point here at 4. And our little rough sketch supports that as far as rising and then falling, signaling a max, falling and then rising, signaling a min. So all of this is adding up in the way that it's supposed to. Yay. All right, and we could make a fairly accurate sketch of the graph as is, but if we want to be super accurate, we have to go one step further and find out where the inflection points are. So let's do that. And it occurs to me I forgot to hide things on this screen. So the hidden information or the important information is that an inflection point, which is like one of these guys, all right, where the chain bending down and bending up, or vice versa, like so. Maybe you're bending up for a while and then you bend down. Okay, those inflection points occur when the derivative changes from where it's increasing to decreasing. All right, let's see that. So right here, the slope's decreasing, now it's increasing. That's an inflection point. Here, the slope is increasing, and now it's decreasing. That also signals an inflection point. Okay, so with that, we can now learn, let me just clean up this screen, we can learn where the inflection points are by looking at f prime and seeing where it changes from increase to decrease, or vice versa, where does it change from decreasing to increasing. All right, so let's go ahead and observe that in our graph of the derivative. Here we go. I'm decreasing from a high number down to a low number down to 0, and now I'm going back up again. So that must be signal inflection point right there. Now I'm increasing. Now I'm going from down towards 0 and down, negative, down, decreasing. And now I'm increasing up towards 0 and up towards the sky again. All right, so what do we learn about the original graph? Well, at that changeover point where it changes from decrease to increase, we expect to see a point of inflection, POI. And that's x equals -2. Increase, decrease, changeover point, x equals 0. Point of inflection at x equals 0. And then decreasing to increasing occurs at x equals 3. So another point of inflection at the point where x equals 3 on the original graph. Okay, so we've got inflection points at -2, 0, and 3. Let's go ahead and fast forward to our summary screen. -2, 0, and 3 are the important numbers where we should expect to see points of inflection. And I believe if we can just collect all this information all together now and put it on a graph, I think we'll be good to go. All right, so here it comes. I'm going to attempt to now draw a graph that has all of these features. It's got to have the right max, the right min, the right inflection points. It's got to rise at the right times, fall at the right times, bend up, bend down. All this information that we've learned through calculus is going to come into play as I try to sketch this thing. So here goes. Right in here, I need the graph to bend like that, and then I need it to bend like that. So let me try to make that happen. Up to here, I'm just trying to signal my important points. So I'm going to bend this way, and then I'm going to bend this way, right up to there. Now I need it to bend like that, have a max, and then bend like that. And I'll again try to mark these important values where interesting changes occur. Okay, so I'm following this bend. It needs to go like that up to there, has a max, and then bends down until we get to 3. Okay, and then to the right of 3, we're going to bend like that. We're going to see a min, and we're going to bend like that. Here goes. Let me label my important point. So we're bending now this way, and then we're bending up like that and off to forever. Okay, so let's go ahead and just check a few things. And maybe I should highlight these important points. So let's see if everything looks right. As far as the information we've collected, we said that the function should increase from negative infinity right up to 1. Is it doing that? Increasing, 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 increasing. Yes, it is. We said that it should then decrease from 1 to 4. Is it doing that? Decreasing from 1 to 4. Yep. And finally, we said that it should increase from 4 off to the right-hand side of the number line, and it does all those things. Let me rewind, and can we check and see if the concavity looks right? Oh, by the way, in terms of increasing and decreasing, we also have this fact that there's a max occurring right here, which there is. There's supposed to be a min right here, which there is. So everything fits so far. And now let's check the information around concavity. We're supposed to see concave down, and this is indeed bending down. It's supposed to be concave down in here. This is bending down. It's supposed to be concave up in this zone, bending up, bending up. Oops. Did I say that the right way? No. Let me roll back a step. So it was actually supposed to bend down all the way up to 0, so that's why it's bending down right here. Okay, so it does agree, I just didn't say it right the first time. Okay, let's keep rolling. So over here we're supposed to be concave up, and that's exactly what you see is a concave up picture. Okay, so this graph, and I'll reverse this so it looks clean. This graph that we've drawn has all the key features that the information in the graph of the derivative conveys to us. And so we feel like we've done a reasonable job in sketching the graph of the original function, which is what we were supposed to do. Okay, so just to go back to the start, this whole discussion was meant to help you understand connections between information in the derivative and information about the original function. And I surely hope that this helped you to learn those concepts. See you next time.